Quantum mechanics is the study of unbelievably small stuff, including light particles and electrons, while being uncertainly certain about it. The double-slit experiment showed that particles at this level behave more like waves until we measure them. Basically, these particles don't have a position until they're measured, but they do have a probability of being found at a position. Schrodinger's wave functions lets us predict these probabilities through time, and they are incredibly accurate. Now, for the standard model, it has definitions for 3 out of the 4 fundamental forces. Bosons, which are force particles, they command the strong force, electromagnetism, and weak force. These are all successfully quantized and they all work within spacetime. But, as Einstein described it, gravity is not necessarily a force, and it doesn't really work within the standard model. In 1915, Einstein proposed his incomplete theory of general relativity, which determined gravity is a result of the curvature of spacetime itself. So, gravity is a result of interactions between matter. If you don't understand that, here's a quote by John Wheeler. Spacetime tells matter how to move, matter tells spacetime how to curve. So, spacetime curves to the matter that's in it, and that's what we call gravity. Now, let's go back to quantum mechanics. It works damn well, it's accurate, consistent, and it's been confirmed plenty of times with experiments. But at the quantum level, general relativity doesn't work. The wave function we talked about before tells us the probability of a particle being somewhere. But according to general relativity, any particle must also have a gravitational pull. So how would we find the spacetime curvature of somewhere? We would need a quantum description for gravity. So let's start from the smallest unit measurable in quantum mechanics, the Planck length. The Planck length is so incomprehensibly small. For reference, the smallest length science has ever measured is 10 to the negative 18th meters, and that was done at this behemoth of technology. We can't measure anything smaller than the Planck length because of these two uncorrelated reasons. One is because the energy to do so would form a black hole, and the other is due to Heisenberg's uncertainty principle. This means that there's a limit to how much we can know. We can either know the position of a particle or how fast it's going, but not both. From these Planck areas and volumes, we can quantize space itself. This means that the geometry that would emerge, it would be discrete, and this would give us the smallest possible spectra instead of a space continuum. So at the smallest scales you can measure, space would look grid-like. We can call each chunk a quanta of space, and the geometry that would come out would fit the discrete and probabilistic nature of quantum mechanics. A good way to visualize it is with the t-shirt analogy. The t-shirt is made up of these tiny little threads, so if you were to take away these threads, there would be no shirt. Rather than this t-shirt being infinitely divisible, there's a point where it stops being a shirt. It no longer exists. So think of space itself as this t-shirt. Space-time is woven by these interconnected quanta of gravity, just as this t-shirt is woven together with these threads. This is the theory of loop quantum gravity. So to calculate these areas and volumes of discrete space, we use the mathematics of SU2. SU2 links the angular momentum of particles to the lattice geometry of space. The probabilities of the way that these particles orient correspond to the discrete space itself. This is because particles at the quantum level have angular momentum, which is there even if the particle is stationary. This is called spin. In spin 1/2 particles, they can be spin up or spin down. Now, when you include antiparticles, they can be spin up or spin down too, for a total of 4 possibilities. Antiparticles are like the evil twins of particles that already exist. When a particle and its antiparticle touch, they annihilate. Their spin states would sum to 0, and they can give off any particles that also sum to 0, as long as everything else is conserved too. But this means that spin 1/2 particles need a 720-degree rotation to go back to its original state. If that doesn't make sense, you can think of it like when you're trying to plug in a USB. You try the first time, it doesn't work. Rotate it, doesn't work. And then you flip it one last time, oh my god, it's in. Then it works. So for loop quantum gravity, these SU2 labels of spin are intertwined together and would make up networks. These spin networks would make up the chunky area and volume of space itself. But if you zoom out a little bit, space would appear foamy. You can call this spin foam, quantum foam, whatever you like. This is because of the particles constantly annihilating with each other and the spin networks constantly changing. So these random space-time fluctuations are what actually progresses the arrow of time. But what does time really mean? The arrow of time is only a concept. But of course we experience time the way we do, but at the quantum level, where space is discrete, we have to change the way we think about time. Time is really a measure of things happening, or events. This makes a lot of sense when you consider the second law of thermodynamics, which states a system's entropy is lower in the past. This is how you distinguish the past from the future. If you try and predict the future in quantum mechanics, you only have a probability. The reason we are able to predict the past is because entropy is always lower. So for loop quantum gravity, time is the evolution of the states of the spin networks. Space is always dynamically changing, similar to how Einstein believes space is. So if we take the bullshit of quantum mechanics, add the possible states of the spin networks, let them evolve through time, we get space-time as we know it. So let's answer the original question. How do we find the space-time curvature of somewhere? We find the somewhere, at whatever state it's in, at the point of wherever that is, when we measure it. Nice. Now we have a theory of quantum gravity, but what does this predict, and how can we prove it? First, white holes. With Einstein's theory of general relativity, we know everything that happens in a black hole right up until the singularity, which is the point where gravity is infinite. With our solution to quantum gravity, we can actually solve what happens inside the singularity. We know the curvature won't be infinite, so what happens? So all of the matter that entered the black hole would eventually come right back out, instead out of a white hole, which is the theoretical opposite of a black hole, where nothing can enter it and it would spew out all of the matter, light, and all of the stuff that entered the black hole. But because of the time dilation, this process would take billions of years for the black hole to fully evaporate and become a white hole. These white holes can be observed by seeing their effects on the things around them or by direct observation. Black holes were once hypothetical too, until we were able to prove that they existed. Funny thing is, maybe we observed them and we didn't even know. On June 14th, 2006, there was a really weird gamma ray burst, GRB 060614. The thing lasted 102 seconds long. Usually gamma ray bursts last under 30 seconds. There was nothing detected in the area, meaning there was no supernova, nothing. There was nothing left over. It was just pure energy, releasing, for the whole duration. If white holes do exist, that's what it would look like. Pretty cool. The Immirzi Parameter. The Immirzi Parameter is a constant that appears in equations of loop quantum gravity. It's a set number because of the theory's ability to predict black hole entropy. Basically, it's proportional to the size of a certain amount of the spin networks. If we were able to find it in another context, it would help experimentally confirm loop quantum gravity. The Big Bounce. In cosmology, loop quantum gravity has a huge purpose for its theoretical work. Rather than the Big Bang, loop quantum gravity would predict a big bounce. Since there's a minimum distance possible in the universe, you cannot have infinite curvature from a singularity. So the Big Bang is replaced by a contracting previous universe getting so small until it reaches the minimum volume, where quantum mechanics would have to take over and then universe would have to leap into the Big Bang. Observing for certain patterns in the cosmic microwave background, explained by quantum gravity, is a way that we can prove or disprove the Big Bounce in the future. In my opinion, this idea of the universe is beautiful. It contracts and beats just like a beating heart. Okay, let's summarize everything that I learned and you learned. Space is quantum. This means that there's a smallest possible measurement for everything. Something can't be infinitely small. This includes time. Time happens because it's the evolution of the spin networks. And then there's nothing past the spin networks. This is the background of everything. Thank you for watching. I hope you learned something new. Don't stop asking questions.